So next I want to talk about the relative strengths of acids and bases. So the Bronsted-Lowry concept introduced this idea of the conjugate acid-base pairs and proton transfer reactions, but we're able to actually understand that some of these acids are what we say are stronger. They more easily give up H+. Okay, so the easier they give up H+, we say that that is the stronger acid. Now we're going to go through later on and we're going to talk about why that is on a molecular level. Okay, but right now we're just going to say that strong acids more easily lose H+ than any other acid. So if an acid loses H+, the resulting anion is now the conjugate base, right? So it's now the conjugate base. So we're going to see that there's a relationship between the strength of an acid and the strength of its conjugate base. The stronger the acid, the weaker the conjugate base, right? Because if the strong acid wanted to give up H+ really easily, well, why would that conjugate base want to take the H+ back? It already wanted to give it up. So we'll see that there's a relationship between the strength of an acid and a base. So again, strong acids have very weak conjugate bases. In fact, we're going to say conjugate acids, their conjugate bases are so weak, they don't even really act as bases at all. Okay? And we're going to say that strong bases have weak conjugate acids. And again, in fact, we're going to say that the conjugate acid of a strong base really isn't an acid at all. It doesn't want to give up that H+ or except that OH. Okay? So here's an example. So perchloric acid is stronger than sulfuric acid, which is stronger than hydrochloric. There's the hydronium ion, that's our acid itself. Then we get into weak. So so above the hydronium ion are all of our strong acids. And below the hydronium ion would be all of our weak acids. Okay? So here we can see that the first acidic proton of sulfuric acid was strong, but now we can see the second acidic proton, right? We lost an H+, so this now becomes HSO4. We lost a plus, so this is minus, so HSO4 minus is a weak acid. Then we have acetic acid is even weaker than that. The ammonium ion is even weaker than acetic acid. And then finally, the weakest would be water itself. Now, remember, when we give up H+, we now have the ClO4 minus, which is the conjugate base. Well, if HClO4 really wanted to give up H+, that means that the ClO4 minus is a really weak base. In fact, we're going to say it's not a base at all because it doesn't want to pick up the H+, right? If it picks up the H+, it's just immediately again going to dissociate. So the stronger the acid, the weaker the conjugate base. And so you'll see that relationship the whole way down through until we get to the strongest base, which is just OH. Right? So that's our strong bases, was the sodium, lithium, potassium, calcium, strontium, and barium hydroxides. So those were our strongest bases. Okay. Okay, and again, the weaker the acid, the stronger the conjugate base is going to be. In fact, we're going to be able to quantify, we're going to be able to relate the acid strength to the conjugate base strength using equilibrium constants. And that's what we're going to do a lot in this chapter here. Okay. Okay, so let's consider a system. We have two opposing Bronsted-Lowry acid-base reactions. We have acetic acid and we have water. Now remember, they can both act as acids. Here's our acetic acid, which is stronger than water. Okay, so keep that in mind. Acetic acid is stronger than water. So basically what that means is we're going to have an equilibrium because they're both weak, right? They're both weak. But in this case, the acetic acid is going to give up to the water, right? And then we have the hydronium ion. So in this case, the water is acting as a base. So I'm sorry, let's go back to this. So we have our acetic acid in its conjugate base. We have the hydronium ion in its conjugate base. So coming back, Again, we can see this time that the hydronium ion is a stronger acid than the acetic acid. Okay, so the hydronium ion is a stronger acid than the acetic acid. So again, we have this conjugate acid-base pair between the acetic acid and the acetate anion, which would be the conjugate base. And again, the second set, which is the hydronium ion, which is acting as the acid, and the water, which is acting as the base. So to understand which side is going to be favored, so is the reactants going to be favored or are the products going to be favored? Does anybody have an idea of which one are going to be favored? Well, the stronger acid's going to want to do its thing, so it's going to push that equilibrium this way. So in this case, there's going to be more reactants and less products. The stronger it is, it wants to push in that direction. So in this case, there's going to be more reactants than there are products at equilibrium. Okay? And again, that's because the hydronium ion is a stronger acid than acetic acid. Now, we're also going to find that certain salts can act as acids or bases, and we're going to discuss that in the next chapter. So we're going to find out that salt solutions, so when you throw, for example, sodium chloride in water, we're going to find that the acidity or basidity of the solution doesn't change. So sodium chloride actually doesn't act as an acid or base. But when we throw, let's say, sodium hypochlorite, when we throw sodium hypochlorite in water, the solution becomes very basic. In fact, if you ever used bleach, all bleach is an aqueous solution of sodium hypochlorite, and it's very basic. But again, we'll discuss why that occurs in the next chapter, why some salt solutions are acidic, some are basic, and some don't affect the pH, the acidity of the solution at all. Okay, so a reaction in which two molecules react to give ions is termed self-ionization. So this is two identical molecules reacting with each other to form ions. An example would be two water molecules reacting with each other. So here we got two water molecules, and they're reacting with one another. One is giving up a proton to the other, right? So one's giving up a proton to the other. So we see that transfer, right? This guy gave a proton to this one. That made that OH minus and this H3O plus. So the equilibrium constant expression would look like this. Now, does anybody see anything funky about this equilibrium expression? All of you should.
It's got two waters as the reactants.
So what are you saying is wrong then?
It just throws me off, I guess.
Well, there would be, so we could rewrite this as 2H2O.
Okay, I guess that's fair.
Okay, so is that okay then here?
Liquids are not supposed to be included in the equations, right?
Exactly. Why? Because they're pure liquids, right? Pure liquids should not appear in the equilibrium constant expression. Now, let me show you why. There is almost no ions in this solution compared to how many water molecules there are. So after this reaction occurs, the concentration of water, and you can actually calculate this for yourself, the molarity of water in pure water. Now, I know that sounds strange, right? But the molarity, you can calculate it. The molarity of water in pure water is 55.5 molar. No matter how much salt you dissolve in it, to a reasonable amount, no matter how much salt or acid-base reaction occurs in a solution, the concentration of the water in an aqueous solution is still 55.5. So it never changes. It ends up being constant. So that's why pure liquids and pure solids don't appear in equilibrium constant expressions, because they're just constants. So basically what we could do is rearrange this equation We could put the H2 over here, which is remaining constant. The equilibrium constant is going to be constant at the same temperature. So we're going to put all this together, and we're going to call that KW. So this is what we call the ion product constant for water. I'm oftentimes just going to refer to this as the, the equilibrium constant for the self-ionization of water. Okay. In fact, I'm probably going to call it that more than I ever call it the ion product constant for water. But it's just the equilibrium expression for the self-ionization of water. Okay. Again, you can see the pure liquid doesn't appear there. Now, why are we making this special now? Why are we calling this KW? Because this is going to be a number that you must know, that we're going to use all the time. You're going to learn this whether you want to or not, if you're doing your homework. If you're not doing your homework, you don't stand a chance. But so if you're doing your homework, you're going to learn it because you're going to use this value all the time. Now, we could write it in two ways, right? We could write it as either the H3O plus and the OH minus, or if we ignored water in it, we could simply show it as the dissociation of water into H plus and OH minus, which really doesn't occur. But again, these mean exactly the same thing because we know that H plus doesn't really exist. It only exists as H3O plus. So you can use either one of these expressions. They mean the same thing, okay? Now, at 25 degrees Celsius, that value is 1.01 times 10 to the negative 14. To make it easy, we're just going to say it's 1.0 times 10 to the negative 14. To make it even easier yet, we're going to say KW is equal to 10 to the negative 14, since it's already 1, right? So that's the value you need to know. KW is equal to 1.0 times 10 to the negative 14 at 25 degrees Celsius. That number will change at different temperatures. Okay, it doesn't change very quickly. So as long as the solution that you're using is around 25 degrees Celsius, plus or minus probably about 25 degrees, KW doesn't change that much. Okay. Okay, so we're going to use KW to calculate the concentration of H plus and OH minus ions in all solutions. So if I know the hydrogen ion concentration, I automatically know the hydroxide ion concentration because of that relationship. That equilibrium constant expression for the self-ionization of water is going to allow us to determine both the hydrogen and the hydroxide ion concentration. But let's do it right now for just pure water, right? So in pure water, since the only thing that's in the water is we'll pretend that it's the dissociation of the water, that means that for every water molecule that splits up, we form one H plus and one OH minus. Therefore, they have to be equal to one another. So in pure water, the hydrogen ion concentration and the hydroxide ion concentration got to be equal to one another. Using an ice table, we'd call them both X, right? And so X squared would equal 1.0 times 10 to the negative 14, take the square root of both sides. That means in pure water, which we're going to call neutral, in neutral water, the concentration of the hydrogen is 1.0 times 10 to the negative 7, and the concentration of the hydroxide is 1.0 times 10 to the negative 7. Okay? So thus, the concentrations of H plus and OH minus in pure water are both 1.0 times 10 to the negative 7. Okay. Any questions about that? Now, we're going to use this as our base then, right? So from now on, when we're talking about either a solution being acidic, basic, or neutral, when a solution is neutral, it has equal concentrations of hydrogen and hydroxide ion, or we could say that it has a hydrogen ion concentration of 1.0 times 10 to the negative 7. That's usually how we're going to look at it. So a neutral solution has a hydrogen ion concentration of 1.0 times 10 to the negative 7. Okay, so then we can quantify this using what we call the pH scale. So instead of always having to use scientific notation, we're going to get rid of that by simply using the pH scale, okay? So the pH is nothing more. P is actually a mathematical term. Does anybody know what P means in math? Simply means the negative log. So if you ever see P in front of some other variable, it just means the negative log. That's all P means. So the pH, H meaning the hydrogen ion concentration, is just the negative log of the hydrogen ion concentration, okay? So let's say, what is the pH of a solution in which the hydrogen ion concentration is 1.0 times 10 to the negative 5? Well, I could already tell you that the pH is 5. The log of 10 to the 5th is negative 5. But remember, it's the negative log, so it's negative times this negative 5, so it's going to be positive 5, right? So again, if you know your properties of logs, you wouldn't even have to plug this into your calculator. You would know that as long as there's nothing here, if this was 2.0, I would know that the pH is going to be 4 point something, okay? And again, knowing that helps you to prevent making little minor mistakes in your calculations. Okay, so again, it's going to be 5.0. Now, the number for sig figs, whenever we take the log, the number of significant digits is going to be equal to the number of significant decimal places. So that's why I wrote 5.00, because there's 2 sig figs in the number in which I'm taking the log, which means it's going to have 2 significant decimal places. Okay. That's what I just said there. Okay, so at 25 degrees Celsius, again, a neutral solution, the concentration of the hydrogen and hydroxide ion are the same. The pH of the solution, so since that's 10 to the negative 7, you can see the pH is going to be +7. So for a neutral solution, our pH is +7. In an acidic solution, our concentration of the hydrogen ion is going to be greater than the concentration of the hydroxide ion, okay? So for example, this would be like 10 to the negative 6th. Since 10 to the negative 6th is 10 times greater than 10 to the negative 7, we can see that for an acidic solution, the pH is always going to be less than 7. And for a basic solution, we know that the hydrogen ion concentration is going to be less than that of the hydroxide. So for example, 10 to the negative 8 is 10 times less than 10 to the negative 7. Well, 10 to the negative 8 will have a pH of 8. So for a basic solution, the pH is always greater than 7. So again, neutral solution has a pH of 7. Acidic solutions are going to have a pH less than 7, and basic solutions are going to have a pH greater than 7. Okay, so just to give you an example, again, you don't need to memorize any of this stuff, but I just want to give you an idea of that just about everything material, food, all of that, it all has either acidic or basic characters. There's very few things that are actually truly neutral, okay? So for example, hydrochloric acid, 1 molar hydrochloric acid has a pH of 0. You can have negative pHs, okay? So for example, when you buy hydrochloric acid, you usually buy it as a chemist or working in a lab. You couldn't do it on your own. There's restrictions. You have to be of a certain profession, okay? You could buy hydrochloric acid at the hardware store. It's called mercuric acid, but it's much weaker than 1 molar. But you can actually buy concentrated hydrochloric acid, which is 12 molar, 12.1 molar. And it has a pH that is negative. It's like -3, okay? So again, you can have negative pHs. On the opposite end, we have a 1 molar solution of sodium hydroxide, and it has a pH of 14. And again, you could have pHs greater than 14. Okay, you can make molarities of sodium hydroxide. You can't go too high because it becomes so incredibly thick, but you could easily go up to about 6 molar, maybe even higher. And again, it's going to have a pH in the neighborhood of 15, 16. So you can have higher and lower pHs, just so you know that. Vinegar, right? So vinegar is nothing more than a solution of acetic acid. It's 5 weight% of acetic acid in water, and it has a pH of 2.9. Carbonated water, so in other words, your soda pop, your beers, anything that's carbonated is actually acidic at 3.9. So this is why it's actually bad to drink a lot of soda or beer. It eventually starts to try to acidify your body. And as we're going to talk later on, the pH of your body, and for example, the pH of blood, I'll talk about here in a second, is about 7.4. And if it fluctuates more than 0.05, you will die. So over time, you keep acidifying your body. First off, you're going to have all kinds of medical issues, but most of those are associated with the fact that you keep lowering the pH of your body, and your blood in particular. So again, that's why it's not good to drink carbonated beverages, because they're so acidic. Beer is better to drink because it's less acidic. So instead of grabbing a soda, grab a beer. It only has a pH of 4.3. Stomach acid is nothing more than a solution of hydrochloric acid. And depending on, whether or not you eat or not, when you eat, you're going to have more acid. And when you're not eating, you're going to have less acid. So when you're eating, your pH of your stomach might be 1. And in those times where you're not eating, the pH might drop down to 3. So again, your body's controlling how much hydrochloric acid is actually in your stomach. Bleach, like I said, this is actually a salt solution. It's a solution of sodium hypochlorite, and it's very basic. It has a pH of 12.6. Then household ammonia, which you would call Windex or window cleaner, is nothing more than a solution of NH3 in water. And again, you can see it's relatively basic, 11.9. In fact, you'll see that most cleaners are bases. So oven cleaner is actually just sodium hydroxide. So cleaners are generally basic. Baking soda. So that's that sodium hydrogen carbonate, right? Sodium bicarbonate, also called, or hydrogen carbonate, sodium hydrogen carbonate. It is almost neutral. It has a pH of 8.4, okay? And that's, remember, we talked about that being able to neutralize either acids or bases, because the hydrogen carbonate is actually amphoteric or amphiprotic, to be specific. It can accept or give up an H+. Milk is actually even better than beer, unfortunately. It has a pH that is almost neutral. It is 6.4. So milk is pretty good for you. And then your blood has a pH of 7.4. So it is relatively neutral, and it really must remain that way. Like I said, if this deviates by 0.05, you're dead, okay? And we'll talk about that in the next chapter. We'll talk about how the body buffers the acid and bases in your body. And a buffer is simply something that stops the pH or prevents the pH from changing that much. And so we'll talk about buffer systems in the next chapter. Okay, so let's do an example. So I want to know, what is the pH of orange juice, given that the hydrogen ion concentration in that glass of orange juice is 2.9 times 10 to the negative 4? Well, again, the pH is nothing more than the negative log of the hydrogen ion concentration. So we're just going to take the negative log of this value, okay? Now, being 10 to the negative 4, I could already tell you it's going to be 3 something. Now, if this was 1 times 10 to the negative 4, I'd know it would be 4. But because there's a non-1 number out here, I know it's going to be 1 less than 4. So I know it's going to be 3 something, and it's 3.54, okay? Again, just knowing those basic facts, if I would type this into my calculator and I would get something that was, 5 here, I know I typed in something wrong and I need to go back and look at my calculator real quick, okay? So 3.54, so that is it. Now, again, we have 2 sig figs in the number that we're taking the log of. That means we're going to have 2 significant decimal places in the value that is determined. So now I want to know, what is the hydrogen ion concentration in human arterial blood, given that its pH is 7.4? So now we're just working backwards, right? So if the pH is equal to the negative log of the hydrogen ion concentration, we want the anti-log, right? So we're going to take the anti-log So we moved the negative sign over, right? We moved it over. That's why we have the negative pH. And then to get rid of the log, we're going to take the anti-log. Now, when it's just written log and there's no base shown for the log, we assume that it is log base 10. So all the anti-log is the base number, and we raise that value to it, right? So in this case, since it's base 10, it's going to be 10 raised to the negative pH. If this was the natural log, well, the anti-log, since the natural log is log base E, this would be E raised to the negative pH, but it's not. It's just the log. So it's a normal base 10 log, okay? So to get that, then we're going to take 10 to the negative 7.4, plug that into the calculator. Now here we have 2 significant decimal places. So that means our answer is going to have 2 significant figures. Okay, so notice how they're consistent going back and forth between logs and anti-logs. So since our number here has 2 significant decimal places, this will have 2 significant figures. And so it's we got to round up, so it's going to be 4.0 times 10 to the negative 8 molar. Okay, any questions on that? Okay. Now, we could also talk about the negative log of the hydroxide ion concentration, again, just so we don't have to deal with scientific notation, and we would simply call that the POH. So the pH and the POH can be related, though, through the relationship, right? We know at 25 degrees Celsius that the equilibrium constant expression for the self-ionization of water is Kw is equal to the hydrogen ion concentration raised to the first times the hydroxide ion concentration raised to the first. And at 25 degrees Celsius, Kw equals 1.0 times 10 to the negative 4. So let's take this part right here, and let's take the negative log of both sides, right? Let's take the negative log of both sides. Well, we know properties of logs. When I have the log of 2 things, let's say A and B, that's the same thing as saying the log of A plus the log of B. But in this case, it's going to be the negative log of A plus the negative log of B. And in here, I have the negative log of 1.0 times 10 to the negative 14. Well, since this is a 1, I know that it's going to, the log would be negative 14, but it's negative, so it's going to be simply 14, right? So that becomes 14. And again, property of logs allowed us to split this up. Well, of course, the negative log of the H plus is the pH, and the negative log of OH is POH. So therefore, at 25 degrees Celsius, the pH plus the POH is simply equal to 14. Now keep in mind, this number really is 1.01 at 25 degrees Celsius, but we're not going to get that picky. Okay, an ammonium solution has a hydroxide ion concentration of 8.3 times 10 to the negative 4 molar. What is the pH of the solution? Well, we got 2 ways we can solve this. One, we could start with the POH, right? Since we got the hydroxide ion concentration, we could determine the POH, so just the negative log of the 8.3 times 10 to the negative 4, which would be 3.08. And then we could use the relationship that the pH plus the POH is equal to 14. Plug that in, right, for the POH and solve for pH. So it's going to be 14 minus, right, we're going to bring it to this side, so minus the POH minus 3.08. And so the pH is 10.92. Okay, and that makes sense because we know that 10 to the negative 4 is much greater than 10 to the negative 7. So that means our hydroxide ion concentration is in greater concentration than the hydrogen, which means we should have a pH greater than 7. Again, you should apply the logic of what you know to determine whether or not your answers are correct. Now, we could have also solved this in another way, right? Since we also know that Kw is equal to the hydrogen times the hydroxide ion concentration, we could have used that equation to determine the hydrogen ion concentration and then took the negative log of that to get the pH again of 10.92. Again, I don't care how you solve problems as long as you solve them correctly. okay? Okay, so measuring pH. So in Chem 110, we talked about using indicators, and we'll talk more about using indicators here too. But really, if you're in a lab, the way you're going to measure the pH is you're actually going to use an instrument called the pH meter. And basically, all you do is you take that pH meter, it has an electrode, we call it the pH electrode, and you stick it into the solution with a thermometer, because remember, it is temperature dependent, pH is temperature dependent, and it's just going to spit out a number for you, which tells you the pH of the solution. So they're very, very convenient. We're going to talk about, in a few chapters here, we're going to talk about exactly how a pH electrode works and all the electrochemistry involved and all the equations involved. And you'll be actually able to calculate then exactly what's happening and see how this pH meter actually works once we get to that chapter. Okay, now we also use acid-base indicators. And remember what an acid-base indicator is, right? It's just called a chromophore. So an acid-base indicator generally is it's either an acid or a base itself, or in sometimes both. If you look back again, I talked about the molecule in red cabbage that acted as an acid-base indicator. And basically what happens is that when there's H plus added to it or H plus is removed from it, the whole molecule changes color, right? And so that's why we call it a chromophore. And in this case, and by the way, there can be different types of indicators too. They don't have to be acid-base indicators. You can have oxidation reduction indicators. In that case, some oxidation state is changing in the molecule and it changes colors. So, but these are specifically, we're talking about acid-based indicators. So all kinds of different acid-base indicators, and it depends on what type of reaction you're looking at. We're going to talk about that here very shortly when we start talking about titration reactions in the next chapter. We're going to come back and we're going to go, okay, what acid-base indicator do I need to quantify this particular acid or this particular base? And we're going to have to choose one that changes color in the proper pH range. So for example, methyl violet changes pH right around a pH of 1. It changes color right around a pH of 1. You have some fancy indicators like thymol blue that actually it changes color at 2 different places. It changes color from an orange to or red to yellow at a pH of 3. And then again, it changes from yellow to blue at a pH of 7. And you could even have it even more finer. So for example, I'm sure that most of you saw like the pH strips that you test either a fish tank or a swimming pool with. And you basically take that strip and you compare it to the different colors on the box. Well, it'll use these types of indicators that have different color shifts. And then you just compare it. And so you can say, oh, it's this color right here. So the pH must be 7.5. Okay. So that's how that kind of stuff works. But you can see you have these, they simply change at different. Another really familiar one, probably you've used this in high school, is phenolphthalein. And it changes pH right around a pH of 9. Okay, it changes color right around a pH of 9. So we'll talk about these further when we start talking about titrations and what indicators we will need to choose to do a titration. Okay. Okay, so again, we're coming back to this idea that the equilibrium constant for the self-ionization of water. But now let's apply it. We've started to apply it, right, in the last couple examples to solutions that were either acidic or basic. But now let's start applying it to actual chemical reactions. So in a solution of a strong acid, so the H plus concentration is usually determined by the strong acid itself. So in other words, we don't need to worry about this, okay? We know that the hydrogen ion concentration is coming from the strong acid itself. But if we want to know what the hydroxide ion concentration is in a strong acid, and there is always both hydrogen ion and hydroxide ion in solution at the same time, always. But when you have a lot of hydrogen ion, you actually have very little hydroxide, and you can still quantify it. You'd simply put in, this would be the concentration of the strong acid. This is just Kw, 10 to the negative 14, and you just solve for the hydroxide ion concentration, okay? So again, I said that, right? It still exists, so we can still determine the hydroxide ion concentration. So here's an example. So I want to know the hydroxide ion concentration in a 0.3 molar solution of perchloric acid. Well, perchloric acid is one of our 6 strong acids, so we know that perchloric acid, when we throw it in water, single arrow, completely dissociates into the hydrogen ion and the perchlorate ion. Well, since this is a 1-to-1 ratio, right, 1-to-1 ratio, I know that the concentration then of the perchlorate, since it fully dissociated, is now the concentration of the hydrogen ion. So this is now 0.3 molar, and this is 0.3 molar, right? Again, because it's a strong acid. I could show that mathematically like this, right? This doesn't appear in your notes. It might, but anyway, it's our 0.3 molar of the perchloric acid. And then from the balanced chemical equation, I could relate the perchloric acid to the hydrogen ion. And again, we can see it's a 1-to-1 reaction. So the perchloric acid cancels, and that leaves us just with the moles of hydrogen. And so that is the molarity, right? So again, you don't need to do this if you understand that this is a strong electrolyte and that it's 1-to-1. For every perchloric acid, we form 1H+. So that concentration will be the same. Okay, so now we can substitute that hydrogen ion concentration. We're going to ignore the 1.0 times 10 to the negative 7, because if I add that to this, right, that's going to be what, 0.3 0.00000001 or 7, I'm sorry. Okay, so way out there, it's totally non-significant. So we're going to ignore that part. So we're just going to say that the hydrogen ion is 0.3. So now we could actually calculate the hydroxide. We're just going to rearrange the equation. So we're going to take the 10 to the negative 14 and divide it by 0.3. And that's going to give us the hydroxide ion concentration of 3.3 times 10 to the negative 14. So really, 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 really small amount of the hydrogen ion in water in an acidic solution. Okay. Okay, so now the same thing is true for the strong base. So for the strong base, again, we're just going to ignore the self-ionization of water. We're going to say in this equation that this is the hydroxide ion concentration due to the concentration of hydroxide from the strong base, and we're simply going to solve for the hydrogen ion. So again, just like we did for the strong acid, we're still going to do the same thing. So here's another example. This time we have a 0.025 molar solution of our calcium oxide. But now in this case, unlike the perchloric acid, if this is 0.025 molar, I got to double it because it's dissociating. Again, it's a strong base, so it's dissociating into 2 hydroxides. So if this was 0.025, that means the hydroxide ion concentration is 0.05. And again, you can calculate it for yourself. You simply start with the concentration of your base, okay? You then relate it, 1 mole of the calcium hydroxide to 2 moles of the hydroxide, right? There's our molar ratio from our balanced chemical equation, just like we've always done before. We get our molar ratios from the coefficients in our balanced chemical equation, okay? The moles cancel, and that leaves me with the molarity, moles per liter, of the hydroxide. So it's double because we have 2 hydroxides. Again, if you know that, you don't have to write this, but if you're unsure, you should write this, okay? Okay, again, we would simply put that then into the expression for the self-ionization of water. So this 0.05 goes here. This is 10 to the negative 14. Rearrange, solve for the hydrogen ion. So it is going to be 2.0 times 10 to the negative 13 molar, this time in hydrogen ion. So there's very little hydrogen ion in basic solutions, and there's very little hydroxide ion in acidic solutions. Okay, start with number 22 from chapter 16. It says magnesium hydroxide is a weak base. A saturated aqueous solution of magnesium hydroxide has a concentration of 3.7 times 10 to the negative 5th molar. And again, this is the concentration of magnesium hydroxide. Now, the important part here is this term right here, saturated. So magnesium hydroxide, as you already know from rule number 8 of your solubility rules, is a weak base, a weak electrolyte, and it is insoluble in water. So that means only a very small portion of it's going to dissociate. And the term saturated means that that is everything that will possibly dissociate has dissociated. Okay, you can't dissolve any more of the magnesium hydroxide and have it actually dissolve and dissociate. So what that means is we have our solid magnesium hydroxide, and we put that in water. Now this is an equilibrium because it's a weak electrolyte. It's going to dissociate into the magnesium 2 plus and 2 hydroxides. And again, because of this term saturated, this is the concentration then of the dissociated magnesium hydroxide. So if we want to calculate the hydronium and hydroxide ion concentrations in this solution, well, it already told us basically what it is. So if I want the hydroxide concentration, well, I know I have 3.7 times 10 to the negative 5th moles per liter of magnesium hydroxide. But I'm interested in the hydroxide, and we could see then from the balanced chemical equation, every 1 mole of the magnesium hydroxide dissociates to give 2 moles of the hydroxide ion. So we simply would going to multiply that by 2, and so then there's going to be 7.4 times 10 to the negative 5th molar. And since this is 2 sig figs, this is exact, that's 2 sig figs. Well, we have 2 molar, or 7.4 molar times 10 to the negative 5th of the hydroxide. Now it also wants the hydronium or hydrogen ion, right? Again, we've used them interchangeably. So we know the relationship is that Kw is equal to the concentration of the hydronium ion concentration times the hydroxide ion concentration. And so to get the hydronium ion concentration, we're just going to rearrange that equation. We're just going to rearrange that equation so that we have Kw over the hydroxide ion concentration. Kw is a value that you need to know. That's 1.0 times 10 to the negative 14. And we just determined that the hydroxide ion concentration was 7.4 times 10 to the negative 5th molar. So just plug that into your calculator. You're going to get 1.35 times 10 to the negative 10. It's to 2 sig figs. So this is going to be 1.4 times 10 to the negative 10 molar, and this would be our hydronium ion concentration. Any questions with that? Okay, let's go to the next one then, number 24. It says rapid release morphine is a narcotic that is used for immediate relief of moderate to severe pain. A solution of morphine has a pH of 9.24 at 25 degrees Celsius. We simply want to know what is the hydrogen ion concentration. So we know that the pH is equal to the negative log of the hydrogen or hydronium ion concentration. Again, we're using the hydronium and hydrogen ion concentration interchangeably. Again, we know this really doesn't exist like this. It only exists as H3O+. So we're going to rearrange this then. We'll move the negative over, so that'll be negative pH, and then we'll take the antilog. And since this is base 10, that means that the hydrogen ion concentration is going to be equal to 10 to the negative pH. So this is the antilog of our negative pH. We brought the negative over. So then we would just plug that in. So 10 to the negative 9.24. Plug that into your calculator. You're going to get a value of 5.754 times 10 to the negative 10. Now, because we have two significant decimal places, our answer will have two significant digits. So this is going to be 5.8 times 10 to the negative 10 molar of our hydrogen or hydronium ion. Hydroxide ion concentration. We could just do this again. We could just use this equation that we used the last time. Or we also know that the pH plus the POH is equal to 14. And so we just rearrange this and say that the POH, actually I'm going to solve this one first. This would be more for this guy down here. Okay, so we could have done this to solve for here, but we could just take the pH plus the POH is equal to 14, rearrange that and say that the POH is equal to 14 minus the pH. So this would have been 14 minus the pH, which was given as 9.24, and that would have simply equaled 4.76. We're considering this to be exact, so this is 2 passed, this is 2 passed, so your answer would have been 4.76. So that would have been the POH. Then we could do the same idea here, right? We know that the POH is equal to the negative log of the hydroxide ion concentration. So we could just say again, we're going to bring the negative over, so it'll be negative POH, and then take the anti-log. So that'd be 10 to the negative POH. So that's going to be 10 to the negative. We just figured it out as 4.76. Plug that into your calculator, and you're going to get a value of 1.737 times 10 to the negative 5. Again, this is 2 decimal places, so this will be 2 sig figs. So this will be 1.7 times 10 to the negative 5th molar hydroxide.